So today's warm-up question has actually two questions, and it says, assuming this marker shows feet, what is the depth of the floodwater? What would you guys tell me the depth is based on what you see in that picture? 2.5 feet. Yeah, about 2.5 feet based on that marker. Okay, would it be reasonable to say that the water has a depth of 2.4973 feet? Could I give you that specific of an answer? No. Okay, I can't tell if it's exactly 2.4973 feet. I can tell it's about 2.5. I mean, maybe that's right. I have no way of knowing with this measuring tool. And that's going to lead us into our notes for today, because we're going to be talking about some different things, some different physics skills, unit conversion, scientific notation, but also accuracy and precision and significant figures. Okay, so that's going to lead us right into this, precision of a measuring device. We have two different measuring devices here. Both of them measure height. This one you might see on the door frame of a Taco Bell or convenience store, and it shows basically every half foot. It's kind of like my flood marker. There aren't very many markings on it. Whereas this one is something you would see at your doctor's office where there was a lot of markings on it. It is a very precise measuring tool. Okay, with any measuring tool that you use, you should always estimate one place beyond the smallest mark on the device, which means that I can't give you 4 decimal places with that warm-up question because I can't see enough to do that. So again, you should only be going one place past what you can see. You can estimate that last digit. Okay, but you can't estimate past that because you can't see past that. So this, again, tool that you'd see at the office is very precise. It has more markings or graduations. That's what those markings are called. There's graduations. That's where the tool that you used in chemistry, you probably used in chemistry, a graduated cylinder gets its name from. All the graduations or markings on it. But more graduations on the device are going to be a more precise device. Heights can be estimated to the nearest hundredth of an inch with this tool, whereas this over here is not precise. There are a few markings on this device, and those heights can only be estimated to the nearest whole inch, because that's the farthest I can see is whole numbers of feet or half of feet. But if I were to take that one place further, I really can only give you the nearest inch. I can estimate how tall this guy is. So if this is 6 foot and this is 6'5", I don't know, maybe he's 6'3". I don't know. He could be 6'2". He could be, something else. I can't tell. But that's the point, is it's not a very precise device, but you can only estimate one place past the smallest marking on your device. Okay, accuracy versus precision. These are terms that you should be familiar with from chemistry if you took chemistry. If you're in chemistry now, then hopefully you're going over it soon if you haven't already. But accuracy refers to how close a measurement is to the true or accepted value. Is it accurate? Is it correct? Is it close to what it's supposed to be? Precision, on the other hand, is how close those values are to each other. Even if they're wrong or right, it doesn't matter. Are you consistent? If so, that means you have precise measurements. And it could be a user error that makes you consistently wrong. It could be a measuring device error that makes you consistently wrong. But if you're consistent, you're precise. So it is possible to have precision without accuracy. Again, you can summarize this like I did here. Thus, accuracy is how right you are in your measurement and data collection, whereas precision is how consistent you are in each measurement. It is possible to be precise without being accurate, or to have an accurate average, even if you weren't precise in individual measurements. So you can end up with an accurate average from multiple trials, even if your measurements are all over the place. You might get lucky. Some of them are too high, some of them are too low. They kind of cancel out. You end up with an accurate average anyway. So again, just definitions you need to know. But we're probably not going to ask you questions about, hey, what's the definition of accuracy? Instead, we're going to ask you to apply it to a scenario where you have a data set, maybe something that looks like this. So this question says, acceleration due to gravity on Earth is 9.81 meters per second squared. 4 physics students conducted an experiment in which they measured the time it took a ball to fall from a height of 4.5 meters and calculated acceleration. Their data is below. And so we have this data table with some accelerations that were calculated by Matteo, Nari, Flynn, and Imani. And I have 2 questions for you. Which student is most accurate? Which student is most precise? I'm going to give you all a moment to turn and talk to your neighbors so that you can discuss and figure out how you might answer these questions. Who is most accurate? Who's most precise? Look back at the definitions if you need to. You have 20 seconds. Go ahead. Discuss. All right, let's see. Any volunteers for who is most accurate? Yes.
Nari is the most accurate because their average ended up being the closest overall to 9.81 over meters over second.
All right, cool. So Nari is the most accurate because her average is pretty much spot on. Do you know who's most precise?
Yes, Flynn is.
Flynn is most precise. Why do you say Flynn?
Because its value is goes in chronological order.
Okay, so his values are in chronological order. That's not necessarily required, but what else can you tell me about his values? Or do you want to add to it?
I can add to it. Because his are in the hundredths place, they're more precise than Mateo's.
Okay.
More accurate.
Okay, so he's got he has a 100th place shown, so sure. Okay.
I think Mateo's the most precise because if he has 2 numbers that are exactly the same and then 9.8.
Okay. So when you're trying to determine precision, ultimately it comes down to consistency. So what you really want to look at is the range of values. How far apart is the smallest value from the largest value? What's that range? And so if you look at those, Matteo has a range of 0.2. Flynn's range is in the hundredths. So his values are much closer together, which means he is being more consistent. And that's going to be the case if you have more decimal places. I mean, it's easier to be more precise. And so he is actually the most precise one up here. Okay, but yeah, Matteo did have 2 that were exactly the same. If they were all 3 the same, then he would have been the most precise because he would have had 0 variation in his measurements. Even though his tool wasn't most precise, he still would have had the most precise answers, at least as he recorded them, if they had all been the same. All right, questions about accuracy and precision? All right. Okay, so again, we looked at some graph interpretation stuff as well. This one's not like a standard graph, and it's not really, this is actually an SAT or ACT science question, sorry. It says approximately what percentage of the human population lives to at least 80 years of age, and what age range shows the greatest increase in percentage of deaths? Okay, so I'm going to give you a moment to look at this graph and to contemplate your answers to those 2 questions, and then we'll come back and talk about it. Yeah, y'all can talk to your neighbor.
Yeah, but look, make 60.
I'm doing the one.
Okay, guys, so what did you come up with? Approximately what percentage of the human population lives to at least 80 years of age? What do we think?
40%.
So here's 80, right? So if we trace this up,
60%? No.
then we're at 60 over here. But what does this 60 represent?
The amount of people that have died.
Percent that have died. Make sure you read your axes. Okay, so if 60% have died, then what population is still alive? 40%. Okay, and then at what age range shows the greatest increase in percentage of deaths? And so if you take a look you're kind of looking where you have the greatest slope, basically, because that's where you're going to have the greatest increase in the percentage, is if you have it happening, quicker. And that's kind of right here, like right after 80. Seemingly, if this graph is accurate, they start to die off slower, actually, after that. But like in this range right here, it goes and it gets steepest about right where my cursor is. So again, just some graph interpretation. We could ask you any graph. It doesn't have to be physics. This is just, can you interpret a graph? Although most of our graphs will, of course, be physics related. All right, you should know your 7 base SI units. We do not use all of these in here, I will say that. But you will, of course, see length in meters. You will, of course, see mass in kilograms, time in seconds. If you took chemistry, you've already seen the mole. We don't use it in here, but that is one of those standard units. Temperature in Kelvin. We don't do a whole lot with temperature in Physics 1. Electric current, though, we will see, and that's in amperes or amps, and luminous intensity in candelas. So again, just so that you're familiar with these, and you guys have access to these slides if you want to go back and copy these later. If I go before you're ready, this is slide 53. You're welcome to go back and glance at it later if you need to. But you really need to know length is in meters, mass is in kilograms, and that's the weird one because it's not grams, it's kilograms. And time is in seconds. Those are the 3 that we use the most. Next semester you'll see amps, but we really don't see much else in here. Okay, unit conversions. So this is something you will need to know, and I have highlighted the obviously most common ones that we're going to use in here. There are others, but you definitely want to know milli, centi, and kilo. Okay, you should have those memorized. You should know what that means if I say kilometer or milligram or whatever. But you do need to report your measurements in units that make sense. You may have to convert values to do this. So like if I asked you how far away you live from school, you're probably not going to tell me how far that is in inches or in millimeters because that would be ridiculous. Okay, and so you want to use units that make sense for the measurement that you're taking. This is more important in a lab setting, obviously, that you use units that fit the data that you're trying to take. But if I did ask you to measure the distance from the school to your house, what would be the most likely unit you would use? Miles, because that's what we use in the United States is miles. So you'd probably tell me how many miles away you live, and that's fine. Now, the metric system, not really equivalent because they're not equivalent to each other, but what you would use in metric system for distances like that would be kilometers. And so that would be what I would expect you to give me if I asked for it in metric units. So if my house is 8,735 meters away from school, how many kilometers away is it? Just a basic unit conversion. This is something that you guys should already know how to do, but we're going to go through this one. Do you have a question?
I know, I was going to answer it.
Oh, yeah. I have it up here, but yeah, if you have meters and you want kilometers, we are going to use a series, well, in this case, just one conversion factor, but we're going to use dimensional analysis to get there. If you have taken chemistry, this probably is bringing back flashbacks because that is how they write it whenever you do your unit conversions in that stoichiometry unit. We're not doing stoichiometry, but we are going to be doing conversions and sometimes a series of conversions, and so this is the way that you might choose to write that. But you're going to be needing to look at the conversion factor from meters to kilometers because I have a value in meters, but I need kilometers, and that's what this table shows. There are 1,000 meters in a kilometer, okay, or 10 to the third if you want to use that. And so I'm going to use that as my conversion factor, 1,000 meters in 1 kilometer, and that means that I am multiplying 8,735 by this fraction times 1 over 1,000, or I'm really dividing by 1,000, which gives me 8.735 kilometers. You'll notice that I also could have done this by moving my decimal place 3 places to the left. If you are dividing by 1,000, that's exactly what you would do. You can see how many places to move it based on this number right here, 10 to the third, 3 places. Okay, so again, you should be able to do basic unit conversions like that one. Standard unit for mass, I had this up here a second ago. I said this is the one that you want to pay attention to because it's a little different. is a kilogram, not a gram. Whenever we use masses in here, they'll be in kilograms. If I give it to you in grams, you will have to convert it to kilograms every single time. If I asked you to measure the mass of a single grain of rice, would kilograms make sense as a unit to use?
No.
Not really. I mean, could you? Sure. Okay, but it's not the unit that I would expect you to use measuring something that small. Now, you might have to convert to it if you were doing a calculation for that grain of rice later on, but if you were just measuring it, I would expect you to use grams or milligrams. If the actual mass of a grain of rice is 0.021 grams, convert this to the standard SI unit, which is, of course, the kilogram. So this is another conversion, this time from grams to kilograms. And we know, again, that kilo means 1,000. It means there are 1,000 grams in a kilogram. And so we're dividing again by 1,000. 0.021 divided by 1,000 is 0.000021, which is why we probably wouldn't use kilograms for rice. Yes?
What does SI mean?
It's the International Scientific Unit, Standard Unit. So, anybody know a better way to write this? Scientific notation. Yeah. Okay, this with numbers that are really big or really small, because there are so many zeros you end up having to write, it's easier to write it in scientific notation. Okay, so if you have values that are really big or really small, use scientific notation. Your calculator is going to do it anyway. It's going to default to it. Or even that Google Sheet that you guys are about to be typing in, it will default to scientific notation if the number is too big or too small to display. So for this value, 0.000021, that is the same thing as 2.1 times 10 to the negative fifth. You'll notice when I typed it in my calculator, I got it in scientific notation already using a TI-83. Again, if you're using the Inspires, they might be a little bit different, or whatever calculator you're using. But if you are using a graphing calculator or scientific calculator, this is the standard way the calculator denotes scientific notation, is with a capital E. So if you see 2.1 e negative 5, that means 2.1 times 10 to that exponent. So 2.1 times 10 to the negative fifth power. So again, if you need to make a note, if you've never seen that before, I'd be surprised if you've never seen it before, but if you haven't, make a note that that's what that E is representing. That is scientific notation. All right, if I tell you that I'm 173 centimeters tall, is this reasonable? Okay, well, you guys may or may not have a very good working knowledge of how much 173 centimeters are, because we typically don't use the metric system unless you grew up somewhere else and maybe you used it. Okay, so if you're not sure if that's reasonable, let's check. We can do a conversion. There are 2.54 centimeters in 1 inch. So I can use that conversion factor. And I can plug in my 2.54 centimeters on the bottom, my 1 inch on the top. And I'm doing that because I need to divide by centimeters to cancel them. Okay, or just think about it logically. Either way, you should recognize this as a division problem. But that means that I would be 68 inches tall. Which is 5'8". So yes, that is a reasonable height. That is my height. So, but if you look at a number, you're not sure if it's reasonable. That's always a good thing. If you do a calculation, make sure your answer makes sense at the end. If you're calculating, the speed of a car and you get 735 miles per hour, you probably did something wrong. Okay, so check for reasonableness. You do want a working knowledge of the approximate size of measurements so that you can evaluate your answers for reasonableness and identify those errors when they occur. All right, here's another one. A student averaged 67 meters per second on a road trip. What is the student's speed in miles per hour? Is this reasonable? So again, we're going to take this 67 meters per second. Because the unit is a fraction, I'm going to put the meters on top and the seconds on the bottom. If you want to put a 1 in front of that S, you go right ahead. Okay, same thing, but 67 meters over seconds. And we're trying to convert this to miles per hour. So that means I have to do both a distance conversion and a time conversion. I'm going to go ahead and do my distance conversion first. I know that there are 1,000 meters in a kilometer. And I know that there are 1.61 kilometers in a mile. Okay, I want this in miles per hour because, again, in order for you to kind of identify whether or not it's a reasonable speed, we need to figure out what that is. And since y'all probably don't have an idea of what 67 meters per second looks like, let's get it into a unit you do know. Okay, so now we have miles, but we have miles per second. Okay, we want miles per hour. So we need to cancel seconds. Again, to cancel seconds, I need it on top because here it's on bottom. So here's my 60 seconds per 1 minute and my 60 minutes per 1 hour. And again, they're set up to cancel units. That's what dimensional analysis is for. You'll notice my remaining units are miles over hours, which is exactly what I want, miles per hour. So now I have a series of conversions that I need to multiply by or divide by. But what you're doing is 67 times 1 over 1,000 times 1 over 1.61 times 60 over 1 times 60 over 1. Or, what I think is easier is just multiply anything across the top and then divide by anything that's on the bottom, however you want to do it. But if you do that, you get 149.8 miles per hour. Do you think that is a reasonable average speed for a road trip? No. Nobody is having that as an average speed unless they're on a racetrack. So this is not a reasonable speed. So now you know if you see a question that says 67 meters per second for a car, it better be a race car or something like that. It gives you an idea of how fast that is. Okay. All right. Percent error. The approximation error in a data value is the discrepancy between the exact value and some approximation to it. We can evaluate how good our data is by looking at how far off it is from what it should be. And that's what a percent error calculation does. Okay, so for example, if the actual mass of the grain of rice is 21 milligrams, but my balance consistently finds it to be 17 milligrams, what is my percent error? Oops, I thought I had it worked out on here. Okay, and so if you wanted to do that, then you would say, okay, my measured value is 17 minus 21, and then that difference, absolute value, over 21 times 100, you get your percent error. And I actually don't know what that one is. I need to work it back out because it's been a year. All right, so let's figure out what that is. So my measured value minus, so 17 minus 21, and then divided by, again, absolute value, but divided by 21. And then for a percentage, we want to multiply times 100. Okay, that's a 19% error. Okay, that's not a very good measurement. So this follow-up question says, is my balance accurate, precise, both, or neither? Well, it's definitely not accurate if I have a 20% error. But it does say that it consistently finds it to be 17 milligrams, so it is precise. Okay, I need to probably recalibrate my balance if I have that. Okay, so again, this is a way to tell if you have accuracy is by looking at your percent error. If you're doing an experiment, you really want your percent error to be within 5%. If you have good data, within 10% for sure. If it's beyond that, then something went wrong somewhere. All right, for the rest of the class period today, I'm going to give you the rest of time to work on the assignment 102.3 graphing and reasoning problem set that is due by 11:59 p.m. Please note that your questions are randomized and will not match your neighbors. So when you read them, you probably have different numbers in the calculations. Some of the questions might be the same. Some of them might have a different graph or a different number. So just be careful as you're reading it. You're welcome to work together, but I would not recommend copying their answer because obviously if they have different numbers than you, then they're going to have a different answer than you. Okay, so that could cause you to lose some points, which you shouldn't be doing that anyway. So you're welcome to help each other out and say, hey, how do you do number 3? But please don't just copy their answer to number 3. All right, guys, go ahead and open it up, get to work. There is a Google form to turn in with it if you have